Alright, so we're going to take a look at derivatives at some point c, comma f of c. So from pre-calculus we saw this thing called the secant line. And a secant line is any line that passes through 2 points of a curve. So we have that first point, x comma f of x. The second point's x plus h, f of x plus h. So the distance between those two is going to be h. And if we actually find the slope of that line, it's going to be f of x plus h minus f of x divided by h after we cancel those two x terms. So again, this is what we call the difference quotient. This is pretty much the last thing that we see in pre-calculus. And we want to, for calculus, turn this thing into a tangent line. And so how do we do that? A tangent line's a line that passes through a single point, whereas our secant line passed through two. So what we can do is we can shorten that h there. And we're just going to keep moving h to be smaller and smaller until eventually it merges with x. So h is becoming 0 pretty much. And so we have a definition. The derivative of f of x is given by the limit as h approaches 0 of the slope of the secant line. And so if we have f of x is equal to 1 over x minus 2, we can find the derivative. First we want to just pretty much find the difference quotient, and then we're just going to take a limit as h approaches 0. Alright, so f prime is going to be our notation for derivative. And our limit definition of derivative, remember, is this thing. So we're going to first have f of x plus h minus f of x divided by h. And we need to find a common denominator on top, which is going to be x plus h minus 2 times x minus 2. We'll try to simplify that numerator there so we can get rid of the complex fraction. And instead of dividing by h, we're going to multiply by 1 over h. And this is what it looks like so far. If we simplify, the 2's cancel, the x's cancel. And we're left with negative h over x minus 2 times x plus h minus 2 times h. And those h's are going to cancel. And now we have this limit. So notice we're not going to get any errors or any issues if we send h to 0. So we're going to apply the limit. And now we end up with negative 1 over x minus 2, which we can simplify. Negative 1 over x minus 2 squared. So there's our derivative, f prime. So we can think of the derivative as sort of this machine. Okay, we take some function, we throw it into the machine, we turn the machine on, and then it spits out a new function that looks a little bit different than before. And what that machine made was a slope of a tangent line. Alright, so we can use that limit definition of derivative, but it turns out to be pretty time consuming. You know, taking limits can be pretty difficult, and so we have a few shortcuts that we want to look at first. So this will be the theorem. Suppose f and g are differentiable functions of x, and c is some real number, just a constant. If we take the derivative, this is our notation d dx of c, so that's our operator, d dx. It's going to disappear once we apply the derivative. d dx of a constant is 0. If we take the derivative of two terms that we're adding or subtracting, we can break it up into two different derivatives. If we have a constant, we can take out the constant and then just differentiate the function. And then lastly, if we differentiate x to the n, it becomes nx to the n minus 1. So these are pretty basic rules for derivative, and we're going to look at just a few examples. Alright, so find each derivative, and we have a bunch here. So first, x cubed, if we want to differentiate that, x to the n becomes nx to the n minus 1. So we're going to bring down that 3, and then x to the n minus 1 is going to be x to the 3 minus 1, so x to the 2. If we differentiate 6, that's a constant, so it's going to become 0. If we think about the next one, we have 4x to the 1. So that's going to become 4 times whatever the derivative of x to the 1 is, which is 1x to the 1 minus 1, which is 1. And so we end up with 4 here. Pi cubed is a constant. Remember, it looks like a variable, but it's not. If we have 10x to the 4, that's really 10 times 4x to the third, and so we get 40x cubed. Derivative of x, it's really 1x, and that's why we're left with 1. Same that the derivative of 2x would be 2, or the derivative d dt of 2t would just be 2 also. And so if you look in the textbook, you can see they do a few more examples when they first introduced these rules. Alright. So find the derivative of f of x is equal to 3x squared minus 2x plus 4. So f prime of x is going to be 3 times the derivative of x squared, which is 2x to the first, minus 2 times 1. And that 4, remember, goes to 0. And so we end up here with 6x minus 2. And this is a little bit different. Now we're going to be asked to find the equation of the tangent line to f of x equals x to the 3 halves plus the square root of x, when x is equal to 4. So remember that the derivative is the slope of the tangent line, and what two things do we need when we find an equation of a line? We need a slope and a point. So we have half of the point, we just have the x value. So let's find the derivative. F prime is going to be, we bring down that exponent, and then we subtract 1. And x to the 1/2 is the square root of x. So it's going to be 1/2 x to the 1/2 minus 1, which is negative 1/2. And we're trying to find the slope of the tangent line at x equals 4. So f prime is the slope of the tangent line. We need to evaluate it at 4. So we get 13 over 4. Okay, so that's our slope. We still need to find the y-coordinate. So if we just evaluate the original function at 4, we get 10. And so here it is. We have the slope, 13 over 4. Our point is 4, 10. And so y minus y1 is equal to m times x minus x1. Our x1, y1 is 4, 10. And our slope is 13 over 4. And so there's our equation. I've posted notes also on Blackboard, and you should take a look at those because we go through different examples and a few more things with derivatives to fully understand them.